Hello, my name is Ning Chen. I am working with Dr. Gang Chen with a project called Uniformity of Gold Nanorods Synthesized by Seedless Growth Method. And I'm here to present that to you. Gold has been regarded as one of the most precious metals in the world since its first extraction in the 5th century BC. It becomes more precious when it's divided into fragments of size, reaching down to 100 nanometer. Gold is one of the most precious materials since early days in human civilization. It is one of the least reactive elements, which makes it solid or tangible to hold under standard conditions. Therefore, gold has been used as worldwide currency as well as a symbol for high class and high social status since ancient time. In nanotechnology, gold nanorods is one type of morphology of the gold metal and is one of the most popular nanomaterials due to its potential in variety of application. Their dimension has a range of 1 to 100 nanometer. Their typical aspect ratio is between 2 to 5. Gold nanorods at different aspect ratio have different color, as shown in the picture. Gold nanorods have a variety of application potentials. One of the potentials in application is display technologies due to its reflectivity alteration when interacting with applied electric field leading to gold nanorods orientation change. Along with other metal nanoparticles, gold nanorods can be applied to be diagnostic agents, monitoring treatment response, and microelectromechanical system. Gold nanorod has its absorption in near IR and produce heat when excited with IR light. This feature can be applied in cancer therapy. Gold nanorods can also have a conjunction with tumor when there is exposed between a patient and IR light throughout body tissues. Gold nanorods can also select tumor cells and destroy them without doing any damage to healthy cells. Another property that gold nanorods have that is that to have advantageous application potential is a localized surface plasma resonance. Localized surface plasma resonance are electron oscillations that are coherently localized, occurring when dielectric molecules have sign changes at the interface of certain materials such as metal dielectric interface and metal sheet put out in the air. Surface plasmon require lower energy than bulk plasmons, which essentially calculate the positive ion cores of longitudinal surface of electron oscillations in electron gas, or as known as plasma. Surface plasmon charge motion can generate electromagnetic field outside and inside the metal. The total excitation containing charge motion of the surface plasmon and the generated electromagnetic field is named surface plasmon polarization. Polariton for planous interface or localized surface plasmon regarding closed surface of small particle. While surface plasmonic resonance is an experimental technique that measures the maximum of the surface plasmon by examining the reflected light from prism coupler as wavelength. This method can be utilized for monitoring thickness, density, molecular absorption changes in nanoscale, so that's why nanorods have been so widely applicable. From UV spectrums, we can easily tell whether the rods are uniform or not by the full width at half maximum of the longitudinal surface of the rods. As can be seen from the picture above, absorption in dotted line on the left picture illustrates gold nanorods in which lower transverse LSPR peak at 512 nanometer depicts while a stronger peak at 780 nanometer shows a longitudinal mode. Adapting Gaussian distribution theory, the narrower and taller the longitudinal peak it is, the more uniform the rods yield. Hence, the full width half maximum of the absorptions is measured to determine the uniformity or monodispersity. There are four main methods to produce gold nanorods: electromagnetic, photochemical, seed-mediated, and template approaches. The most common approach to obtain high quality of gold nanorods is the seed-mediated growth technique. A conventional method entails the mixture of gold nanospheres that are citrate coated, acting as seeds to gold growth solution. The seed solution normally involves cetyltrimethylammonium bromide or CTAP as a surfactant, a gold salt, and a sodium borhymide as reducing agent is increasing overall ionic strength of the reaction. The growth solution is typically involved with the reduction of the gold salt by reductants such as ascorbic acid or hydroquinone in our experiment. With the presence of the CTAP served as surfactant and silver ions, silver compared to gold has a lower reduction potential and form a monolayer on the surface of the gold rods. This deposition slows down the growth rate of the crystal facets, give the orientation to one-directional growth and formation of rods. The high uniformity synthesis in this article involves adding silver ions to the seeds synthesis that help with the one-directional growth from the beginning, resulting in rods instead of sphere formation in seed solution. However, recently a simpler method has been developed. Is seedless gold nanorod synthesis. This seedless approach entails only one step with similar reagents in the growth process of seed-mediated method. To form a gold nanorods, sodium borhydrate is added directly to the growth solution, which contains CTAP, gold ions, namely the gold chloride, tetrachloride, silver ions, namely silver nitrate, and a base, namely a sodium bicarbonate, and a wick reducing agent. In this case, we use hydroquinone. However, seedless method generates a really high polydispersity, which contains a large amount of spherical gold nanoparticles. And that is one problem that we are focusing on today. To tackle how uniformity regrowing method has been applied and developed to seedless gold nanorods, from Lamer mechanism, there are, as you can see from the left picture, there are two stages of growth process. Focusing stage, where there is a rapid increase in size that narrow down the size distribution. A defocusing stage, where there is a rapid decrease in growth rate that widen the size distribution. This defocusing stage is due to Oswald ripening, where large particles obtain, as you can see on the right side, on the right picture, Oswald ripening, where large particles obtain atoms from smaller particles that are dissolving. These two stages rely on seed concentration added in the solution. At high concentration, during focusing stage, smaller nanoparticles grow more rapidly than the bigger ones. When the seed concentration is depleted, smaller nanoparticles need to start to give atoms to larger nanoparticles and start to dissolve, which essentially widen the size distribution. In that case, refocusing the size distribution can be done by changing the reaction kinetics, namely adding more concentration of seed or monomer solutions. Therefore, we believe this refocusing stage can be applied to a weld solution with synthesis to narrow down the size distribution. According to the results from our lab's past project by Dr. Zhang, we found that tuning base concentration or controlling pH, seed concentration and ratio between CTAP and seed concentration in growth solution can improve the uniformity of the gold nanorods with the seed-mediated method. Therefore, we believe that adding a weld solution to seedless gold nanorods solution while controlling pH, seedless gold nanorods solution, and the ratio of the CTAP and seedless gold nanorods solution can improve even further the monodispersity of the gold nanorods. Excuse me. After many trials and errors, these are the results that we got, and those are the most optimal results so far. As you can see on the picture on the left, 10 microliter of the sodium borohydride has the least full width half maximum at 443 nanometer as compared to other variation of sodium borohydride. From addition of 50 microliter and up, nanorods will no longer form since there's no sign of longitudinal peak around 780 nanometer. Instead, strong peaks of transverse peak was shown at 512 nanometer, indicating spheres in particles. Look at the 25 microliter sodium borohydride solution in the trial. Longitudinal peak was formed, but transverse peak was very high, indicating its low yield and less uniformity. Therefore, an optimal amount of sodium borohydride is proven to be 10 microliter. However, keep in mind that the full width half maximum is at 143 nanometer, which we believe is not of a high monodispersity. With that optimum sodium borohydride amount, we added a regrowth process after that, and we used that optimal sodium borohydride of the seedless solution. And the regrowth nanorods with the variation of nanorod solutions show a UV spectrum that yield rods with both transverse and longitudinal peaks. The full width half maximum is at 95, 91, and 92 nanometer variation of nanorods at 0.1, 0.25, and 0.5 milliliter, respectively, are all under 100 nanometer, which is considered narrow and uniform of nanorods, which compared to the seedless solution alone, we can see that is already more monodispersed than the seedless solution. In this picture, all of the solution of the trial yield rods with both clear shown transverse and longitudinal peaks. However, there are two longitudinal peaks of the ratio of CTAP, 9 milliliter of CTAP and 1 milliliter of the seedless nanorods, and 9.2 CTAP with the 0.8 gold nanorods seedless instead of 1. This occurrence can be due to the wide range of aspect ratio leading to the uniformity of the results, or perhaps were due to pipette transferring and technique errors. Although full width half maximum was under around 100 nanometers, specifically 98 nanometer, 108 nanometer in the 9.75 CTAP ratio with the 0.25 of seedless growth nanorods, and the 9.5 CTAP ratio with the 0.5 seedless gold nanorods, respectively. The results were not trustworthy. Errors were confirmed by the repeated trial. The shifts are all consistent though, but there were no true peaks of any solution, which means that the transferring technique needed to be improved. From repeated trial, we see the peaks were consistent and showed nanorods around 780 nanometer, but most of them were not able to show reaction advance. So they were not able to be normalized. Nonetheless, 9.9 milliliter of CTAP ratio with the 0.1 seedless gold nanorods has a full width half maximum of 98 nanometer, which was normalized correctly and shown uniformity. After repeating the reactions, although the shifts in the peak wavelengths are consistent, it is hard to reproduce the trial. So the TEM image of the 9.9 to 0.1 CTAP and seedless gold nanorods ratio, verifying that the result was indeed uniform, so regrowth actually works. Ultimately, a seedless synthesis alone, even with the optimized concentration of sodium borohydride, has a wider size distribution of 143 nanometer in full width half maximum than a seedless synthesis followed by growth step with controlled concentration of reagent. This regrowth process gives an gold ions addition together with atoms from dissolving small particles that refocuses on the growth process of the bigger particles, which essentially narrow the fluid half maximum and boost its molar dispersity. Base or pH, CTAP, and seedless gold nanorods solution ratio, and the seedless gold nanorods adjustments have all been a contribution to controlling the uniformity as predicted. With optimal concentration added, full width half maximum could be narrowed down to be lower than 100 nanometer that shows high molar dispersity. These are the references that I used throughout the seminar presentation. I have a special thanks to Dr. Danton, who has given me a lot of opportunities to work in his lab and to learn under his wings. A special thanks to Dr. Sing Jiang, who has been closely supervised me and helped me with every possible ways, every question that I can ask in the lab, and always support me by answering so many stupid questions. Reese Gallagher, who is not in the lab anymore, but has been a mentor to me since beginning. And thank you to you for listening. Thank you.